So in section 15.2, we're going to discuss how to evaluate limits of a function of 2, 3, or as many variables as you want. All right, there's no limit, no pun intended here, okay? What else? We will discuss the continuity of a function of 2 or more variables, as well as define what we call interior point, boundary points, and well, when it comes to regions, it could be open or closed, and we need to understand this idea about the boundary points and the regions to evaluate sided, what we call sided limits in two variables. But that's going to be a little different, well, a lot different than the usual. So first of all, let's recall the definition of a limit from back in calculus 1, where, well, the limit of the function f of x as x approaches c equals to L, and well, if and only if there's an epsilon, blah blah blah. You might remember this nightmare, this epsilon delta nightmare in calc 1, right? That even that scares a lot of people. Yes, it scared me at first when I took this class, and I'm not gonna lie. But in the end, this is just the formal way to describe the limit that for every delta corresponds an epsilon. That is, if you're finding the limit approaching c, if you go some units away to the right or to the left, well, so the idea that the limit exists if you approach the same y value from either side. All right, so this plus minus delta has a plus minus epsilon. Well, no wonder we have this compound inequality that creates that plus minus, as we discussed with the previous functions in the previous section. So, and again, well, in this case, the function does not have to necessarily be defined at that value of x, you know? So, that's because we're finding the limit, and evaluating limit, it's not the same as evaluating finding the value of a function. Again, evaluating f of x, which is defined or undefined, means can you step on that point, versus finding the limit is where are you going to as you approach a given value. Even though algebraically they look similar, you evaluate, substitute, blah blah blah, and if you get an indeterminate form, you work through the algebra, right? Okay, but let's define the limit of a function in two variables. So here is where it gets more interesting. And again, well, so let's look at two variable case. So for a function f of x, y, as number one, x approaches x naught and y approaches y naught, equals to L, and while the epsilon delta definition looks a little weird, look at that radical x minus x naught squared, y minus y naught squared. That looks a lot like the equation of a circle, all right? Somehow. Well, a circular inequality of radius varying between 0 and delta. But where is that circle coming from? Well, let's look at the definition. So let f be a function of two variables defined except possibly at the point, because again, we don't care whether the function is defined. We're finding a limit on an open disk center at x naught, y naught. This is different this time as opposed to centering a limit at a value for a function of one variable for two variables. Okay, check this out. So we want to approach this point, all right? So, for instance, again, in Calc 1, for limits in Calc 1, you either approach from the left or you approach from the right. How about that? Here is the thing. For functions of two variables, you can approach this point from the left, from the right, all right? You can approach this point from the top, from the bottom, like this, like that, or by means of a diagonal line as well, like this, which is, and well, regardless of the path that you choose to approach that point, well, this is what creates this open circle right here, right? It's no longer an interval plus minus delta anymore. It's actually an open disk of a radius delta. That's what it is this time, right? So, and for instance, okay, let me get rid of all this. You can approach this again from the left, from the right, top, bottom, I can use another curve like this curve and get to this point like this. I can get to this point using this diagonal line right here. I can use an exponential function to approach that point, maybe as long as the function we choose contains the point we're approaching to for the limit. So here, when it comes to boundary points and interior points, because this region are going to be bounded by some level curve, if you will, by some curve in this case. And well, all those points that lie inside the region are called the interior points, and all points that lie on the boundary are called boundary points. So if you can think of this like a sphere, for instance. So a sphere who has a circular projection has boundary points that are defined in like, for instance, x squared plus y squared equals to 1, like plus z squared equals to 1. That's the unit sphere. So the unit sphere has a circular projection having all the points on the boundary, as opposed to, how about I turn this equation into an inequality, x squared plus y squared plus z squared equals less than or equal to 1. In this case, this sphere will project a circle, the same unit circle. However, in this case, because it's less than or equal to 1, this inequality describes not only the points on the boundary, but also describes the points inside the region, right? The interior points. And if this inequality symbol is just less than, this will be simply a dashed circle, right? So that'll be the points that are inside the sphere, but not on the sphere, or in the xy projection, the interior points only, but not the ones on the boundary point. So again, the inequality symbols will tell us everything. All right, now to calculate limits, so let's have a look at the notation. Very, very important notation. I mean, a, b, and c are constants. Well, if we evaluate the limit of a constant c at the point a, b, that's going to give us the constant. If we evaluate the function x, the function f of x equals to x, and at the point a, b, all we're doing is evaluate x equals to a, that's going to give us simply a. And likewise, for f of x, y equals to y, all we do is substitute the y. Again, in a way, it's like evaluating functions, but we're really evaluating limits. All we do is the direct substitution for the corresponding variable, like plug and chug. That's all it is. What else? The properties of limits, or limit laws. So if we have two limits, limit of f of x, y equals to L, and limit of g of x, y equals to M. Two different limits. Same. The limit of a sum is the sum of the limits. Like in Calc 1, you have two expressions, you add the limits for each. The limit of a difference, the difference of the limits. The limit of a function times a constant, it's the value of the limit times the constant. And the limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, provided the limit for the denominator is not equal to 0, because you know the whole story about it, right? The limit of a power, it's the power of a limit. The limit, and of course we can have the square root. Limit is the same, the end root, not just the square root. It's the limit of a square root, it's the square root of the limit. In the same way that if you have limit of, say, e to the f of x, y, this is e to the limit of f of x, y. Which is not necessarily limit, right? Which is not necessarily a trick. It's actually, the limit's at the top there. It's using the properties to evaluate some cases using the L'Hopital's rule when you have this exponential weird case, all right? Well, of course, how about we evaluate limits? Let's just see them. Limit of 5x squared over x squared plus y squared as x approaches 1 and y approaches 2. So, number one, all we do, first of all, every time we have a limit problem, direct substitution. Maybe we're lucky, we get a number, that's the limit. Otherwise, we look for alternatives. So this means, so 5 times 1 squared over 1 squared plus 2 squared, that equals to 1 squared, which is 1, times 5, that equals to 5. 2 squared equals to 4 plus 1, that equals to also 5. And the limit is 1. That's it. Right? What about number 2? Oh, you need to be careful with number 2, because limit of f of xy equals to 1 over x squared plus y squared. By direct substitution, we get the following: 1 over 0 squared plus 0 squared, which is 1 over 0. Huh. Interesting. Not undefined. Undefined is for functions. Functions are defined or undefined as opposed limits who exist or do not exist. Even though, again, the mechanics look very similar, substitution, etc., but the concept behind the way we distinguish between the two is just this vocabulary. What about this one? What's 1 over 0? Not undefined again. What would you do in a situation like this? Well, L'Hopital's rule does not work while we have two variables, so that's going to be a limitation. However, I'm going to show you a trick to use L'Hopital's. It's not on the textbook. I don't think I've ever seen it in any textbooks at all. So I figured it out and it works. So I'll show you that later. But so yes, in this case, yeah, L'Hopital's rule wouldn't have worked because we don't have the indeterminate form. 1 over 0 is not one of the indeterminate forms. Any ideas? What about it?
Maybe partial fraction decomposition?
Partial fraction decomposition, whoa, with... But still, that's not going to cancel anything out, you know? So... yeah, it would be an interesting problem, partial fraction with two variables, maybe making y the constant, maybe, yep. But well, what's the approach in Calc 1 whenever you had the number over 0? Equals infinity. Okay. We need to be careful because it could be infinity or it could be negative infinity. However, guys, rest assured, every time you get a number over 0, at least in Calc 3, and for the homework, just go about D&E. In some cases, like this case, it's possible to analyze the function because the function is relatively simple to analyze. For instance, z equals to 1 over x squared plus y squared, okay? If we get the traces, the y, z trace, that's going to give us z equals to 1 over y squared. If we do the, what's the other trace? The x, z trace, that's going to give us z equals to 1 over x squared, all right? So can you recognize this graph, these two curves? These are curves, no longer surfaces. Don't they resemble like f of x equals to 1 over x squared? Whose graph looks like this. And in this case, if we analyze the function, the limit, the side limits, both side limits agree to positive infinity. So in this case, it's possible to say that it's going to be infinity. All right. However, in this case, we're just going to go with the D&E. You don't have to do this analysis, especially because if we get to more elaborate functions, and we will, there is no way we can easily get the traces and analyze each direction. So that's going to look like this. So like a volcano here, right? It's going to look like a volcano. And yes, from either side, where is that going? Isn't that going up to positive infinity? So in this case, it's possible to analyze a function. All right? All right, so let's have a look at another example. What about limit x squared minus y squared over x minus y as x approaches 2, y approaches 2? Okay, so number 1, direct substitution. 2 squared minus 2 squared over 2 minus 2. That equals 4 minus 4 over 0, which is 0 over 0, which is good, finally. All right? So that means we can use any algebraic technique we can think of to simplify the expression in the limit in a way that we can get rid of those two factors that are causing the troublesome 0 over 0, and then we will be able to value the limit. What about the numerator? Doesn't that look like a difference of squares? So, okay, let's go about it. Limit. So, here is the thing. Notice the notation in the notes, and that's the same notation in the textbook, in MyMathLab as well. So I'm going to use a different notation because this is going to use a lot of space. I'm going to do x approaches to y approaches to. That's also a valid notation. That actually saves space. Well, let me factor the difference of squares, x minus y times x plus y, and that over x minus y. Do you see how the x minus y cancel? Keep writing the limit symbol. Notation matters. X approaches 2, y approaches 2 of x plus y. And because we no longer have denominators at all that cause a 0 in the denominator, we're safe. And we may try direct substitution, and I'm pretty sure this is going to work. 2 plus 2, and the limit is 4. All right? Okay, let's have a look at another example. Every time we have a limit problem, we should try direct substitution. Actually, it's a must because you need to show what indeterminate form to justify that you can do any algebraic trick in here. Okay, so that is, that's 4 plus 4 times negative 1 over 4 squared plus 5 times 4 times negative 1 plus 4 times negative 1 squared. Okay, so in the numerator, that's 4 minus 4. That's going to be a 0. And in the denominator, what do we have? So 4 squared, which is 16. Okay, so 16 plus, or rather minus 20, plus a 4. So 16 plus 4, that's 20. Minus 20, 0 over 0, which is good. All right? That's good. That means we can do some algebra to compute this limit. All right. Oh, how do we compute this limit anyway? We have polynomials in the denominator with two variables at the same time. How do we factor this one? Yes, we can factor it because it's polynomial. Well, so when you have two variables at the same time, let me do this at the bottom. Okay. Ignore the y variable for a second and just write x squared plus y plus 5x plus 4. And factor this trinomial using the double bubble method in this case because that's a leading coefficient equal to 1. That is, factors of 4 that add up to 5, that is plus 4 plus 1. Okay? So I'm gonna put the y's back in. Where am I gonna put the y's? Right here, multiplying with the numbers 4 and times 1. That's how we factor a two-variable trinomial. Make it a single variable and put the second variable at the end. All right. So let me go back to limit as x approaches 4, y approaches negative 1. And that is x plus 4y divided by x plus 4y times x plus 1 times y, which is simply y. Okay? Oh, do you see this? The x plus 4y goes away, which is what was causing the troublesome 0 over 0. And that's going to leave us with limit x approaches 4, y approaches negative 1, and that's 1 over x plus y. And that equals simply substitute 4 for x and negative 1 for y. That is 1 over 4 minus 1, and that equals 1/3. As you can see, we were using the same thinking as back in Calc 1 and Calc 2 when evaluating limits using the L'Hopital rule. We haven't used the L'Hopitals yet, but actually the techniques. Actually, letter E is going to be a very interesting one. You'll see. Okay, so again, direct substitution. Using direct substitution, that's going to give us 18 times x, which is 9, times y, which is 1, minus 2 times x, careful, it's 9 squared. Everything divided by 3 times the square root of y, which is 1, minus the square root of x, which is 9, the square root of 9. And let's simplify all this madness here. So number 1, that's 18 times 9, a big number, that is 162. And then 2 times 9 squared, that's 9 squared, which is 81. 81 times 2, that's another 162. Divided by 3 times 1, which is 3, minus 3, which equals, oh, this is 0 over 0, right? That means we have a case, all right? We have a good case for algebraic simplification. Let me actually rewrite it. I'm gonna need it. X approaches 9, y approaches 1. So that's 18xy minus 2x squared. And then divided by, what's that? 3 root of y minus root of x. And that not equals. Okay, what can we do about this limit? So the fact that we have a 0 over 0 means we can divide out two factors that are causing the 0 over 0. Notice we have radicals, right? Notice we have a common factor in the numerator. Let me take that common factor first. So that is equal to limit x times, actually 2x. Let me factor 2x. 2x times 9y minus x divided by 3 square root of y minus square root of x, as x approaches 9 and y approaches 1. Okay? Anything else we can think of for this buddy right here? What do you think of when you see radicals in a limit problem? Multiplying the numerator and the denominator by the conjugate, which is known as rationalizing the denominator, right? In this case, it could have been the numerator, but I mean, in this case, it's the denominator. However, that's a little long because it's going to get really messy, especially if you can't identify the difference of squares to simplify the work. I'm going to show you a different trick. Let's have a look at this expression inside of the parentheses in the numerator. This is a difference of squares, all right? You may argue, no, it's not, because y is raised to the first power and x is just raised to the first power, right? But still, let me write it like a difference of squares. Limit as x approaches 9, y approaches 1. Yes, of course, everything can be a difference of squares if you want. Why not? What quantity squared equals 9y? Isn't that 3 root of y rather? Quantity squared minus what quantity squared equals to x? Isn't that square root of x? 3 root of y minus root of x. Can you see it now? I'm going to turn it like a difference of squares, factor the difference of squares instead, and that denominator is going to go away. That's the limit. X approaches 9, y approaches 1. That's 2x. Factor the difference of squares. 1 plus, 1 minus, 3 root of y, root of x, 3 root of y, root of x. Divide everything by 3 root of y minus root of x. And no rationalizing the denominator. This is a lot quicker. Of course, If you prefer doing the rationalizing the denominator, do you feel more comfortable with that method? That's fine. As long as you get the same result and you don't make up your own rules, that's fine. Okay, so that's limit 2x times 3 root of y plus root of x. As x approaches 9, y approaches 1. We're good to go and simply substitute, do the direct substitution. That's going to give us 2 times 9 times 3 root of 1 plus root of 9. So that is equal to 18 times 3 plus 3, which is equal to 18 plus 18 times 6, which is 108. Which one?
It was the two numbers were supposed to be subtracted.
This one?
Yeah.
Oh no, it's multiplication. 2 times x, yeah, maybe, yeah, like this. Looks bolder. This one?
Two radical numbers in the parentheses were supposed to be subtracted.
Subtraction. Oh, okay, so here this difference of squares gave me the plus and the minus. We divided out the factors with the minus, we remained with a plus. So that's why we add them here, right? So that's 108. Of course, let's have a look at the next example where we have this time 3 variables, right? So a limit with 3 variables. We're going to use special limits you learned back in Calculus 1. Okay, so of course, that means by direct substitution, e to the z, that is e to the ln of 4, sine of x, which is 0, everything divided by 0 times y squared, that's 2 squared. Okay, e to the ln of 4, that's 4 times 0 over 4 times 0. Careful, this is not equal to 1. This is 0 over 0, which is good, because that means we can do some algebra. However, if we think about this, we cannot factor anything, right? We can't factor to divide out the 0 over 0 because we don't see a difference of squares. Also, we cannot use the rationalizing of the denominator or numerator because we do not have any radical expressions. What else? Maybe complex rational expressions. No, we don't have fractions contained inside fractions, so what can we do about it? So the last resort would be the L'Hopital's rule. However, L'Hopital's rule, it's not going to work, not for this case, at least when we have limits with multiple variables. What are we going to do? Use the properties of limits. Notice we have product, quotient, we have a bunch of stuff. I'm going to group. I'm going to make this big limit and I'm going to write it into the product of two limits. That is, limit x approaches 0, y approaches 2, z approaches ln of 4, e to the z over y squared, and I'm going to group it with the limit, again, x approaches 0, y approaches 2, z approaches ln of 4. I know we need to write all this notation. The notation matters. So only until we substitute, until we do the direct substitution, that's where we no longer write the limit. Sine x over x. Okay. Let's evaluate the first limit. E to the ln of 4 over, what's that? 2 squared, right? Oh, come on. 2 squared. But what about the limit in the second expression? Sine x over x. Do you recognize that limit? What is that equal to? That equal to 1, right? It's one of those limits you learn at the beginning of Calculus 1. You use it to, I think, for the squeeze theorem. Okay, so that's equal to 1. So that equals, boom, boom, 4 over 4 times 1, 1 times 1, and the limit equals to 1. How about that? All right? Okay, what's next? Okay, for the next topic. The next topic is finding limits, different paths. Remember how we approach from the left, from the right, from the top, from the bottom, along a diagonal. I think I'd rather do that later. Because it's gonna take me a good minute to go about this one to discuss every single case. Also, the next topic it's about continuity. I think I'd rather skip it for today. We're gonna come back later because I want to make sure I get to more limits where I'm gonna show you the trick to use the L'Hopital's rule for this beast we're about to see. All right. Because yeah, there's a take-home quiz today with a limit problem where you will have to use the L'Hopital's rule. It's 2 questions only, it's just 1 paper. Okay, evaluate the limit 1 minus e to the 2x plus y raised to the second over sine squared of 2x plus y. Direct substitution, that is 1 minus e to the 2 times negative 1 plus y, which is 2, squared over sine squared 2 times negative 1 plus 2. Okay, in the numerator, the exponential 2 times negative 1, that's a negative 2. That is negative 2 plus 2, that's 0. 0 squared equals to 0. Sine squared of 0. Okay, so sine of 0 is 0. 0 squared is still 0. E to the 0 is 1. That is 1 minus 1. That equals 0 over 0. All right? Okay. Here we're doomed, right? Because there's no way we can do any factoring to divide out that factor that's causing the troublesome 0 over 0. We cannot do any rationalizing of a denominator numerator, no complex rational expression, so we're screwed here. But not really, because check this out. Do you notice this 2x plus y right here? 2x plus y? It's the same expression. So we're going to turn this limit expression in 2 variables, the limit problem in 2 variables, into a limit problem in 1 single variable. That's going to be our way around till we can use the L'Hopital's rule. But this works only if you see a repeating pattern, a repeating expression, okay? So let's see how we're going to do that. Remember the u substitution you usually do when integrating? Well, so we're going to call this u of x, y, because yeah, it's based on x's and y's. And u of x, y will be the expression I just highlighted here. That is 2x plus y. And then I'm going to evaluate this expression u of negative 1, 2. That is 2 times negative 1 plus 2. So u of negative 1, 2 equals to 0. Let's do the u substitution. So that means this limit right here will become the limit as u approaches 0 of 1 over e to the 1 minus e to the u squared, all right, divided by sine squared of u. And magic. That's how we turn a two variable problem into 1 single variable problem. Here we don't have any limitations as to what we can do to evaluate the limit. Again, we already exhausted all the potential techniques to compute it. This is good to go to do the L'Hopital's rule. And in this case, you don't need to show the 0 over 0 again. You already did it in the very beginning. So it will be redundant to show it again. All right? So, L'Hopital's limit as u approaches 0. Okay, so the derivative of the numerator divided by the derivative of the denominator. And again, this is not the quotient rule. I've seen it before. So here's a funny thing. When we're doing L'Hopital's rule, where we do the quotient of the derivatives, a lot of people do the quotient rule. When we first learn the quotient rule, we do the reverse, the quotient of the derivative. So careful. Okay, the derivative of this, the derivative of 1 is 0. The derivative of the exponential, that's a mini chain rule. That's negative e to the u squared times the derivative of u squared, which is 2u, divided by the derivative of sine squared, another mini chain rule that 2 comes to the front, sine u times the derivative of sine, which is cosine u. All right? A couple things. Let me take out that negative 2 outside of the limit expression. That's negative 2 limit u e to the u squared over. How about the denominator? Do you recognize 2 sine u cosine u?
That sine 2x.
It's a double angle formula for the sine function, right? And you might want to do this because it turns out that we will have to do L'Hopital's a second time. And yes, for the numerator, there will be no way around. We'll have to do another product rule. But in the denominator, you might want to save a product rule by using identities, okay? So that is, what's that? Yes, I know, I could have just canceled these 2's right here, but I only took the negative 2 from the numerator to use the double angle for sine. Okay? So u approaches 0 in the numerator. So if we do 0 times e to the 0, that's 0 in the numerator. Sine of 2 times 0, that's another 0 over 0. So we could keep going about the L'Hopital's rule. Yes?
Because you factored out the negative 2, should it be negative sine 2u on the bottom?
No, because it's only, I just factor out the one from the numerator.
Oh,
Yes. Unless I had another one in the denominator, so they cancel that as well. All right? So L'Hopital's that means, okay, so that is negative 2 times the limit as u approaches 0. Okay, product rule, the derivative of u, which is 1, times the exponential e to the u squared, plus the derivative of the exponential, careful here, that is itself e to the u squared times 2u times the u. And in the denominator, no product rule because using the identity was a smart move, so we just do a basic chain rule here, that is 2 cosine 2u. How about, let's combine like terms or simplify this a little bit. Negative 2, limit u approaches 0, that's e to the u squared plus 2 u squared e to the u squared divided by 2 cosine 2u. Let's see if we can simplify, or rather if we can apply what's it called, the direct substitution, so we don't have to do, to determine whether we have to do a third L'Hopital's rule. So in the numerator, that's e to the 0 squared, that's 1, plus 2 times 0 times e to the 0 squared, well, that's going to be a 0, so it's going to be a 1 in the numerator, so we're good. In the denominator, cosine of 2 times 0, cosine of 0 is 1 times 2, we're good, right? Actually, we can divide out these 2's already, so negative e to the 0 squared plus 2 times 0 squared e to the 0 squared over cosine 2 times 0. That equals 1 plus 0 over 1, which is, don't forget the negative, which is negative 1. So negative 1 is the limit here. All right. How much time do we have? I think we can make it. Let's do another one where we will use maybe not the L'Hopital's rule, but at least we're going to simplify the work by at least doing a u substitution here. All right? Because what happens if you do the direct substitution? So that's the square root of 2 times 1 minus 2 plus 2 cubed times 1 cubed minus 8 square root of 2 squared times 1 squared minus 4. Okay, the right hand in the numerator, 2 times 1, which is 2. 2 minus 2 equals to 0. Okay, that's the square root of 0, which is 0. 2 cubed times 1 cubed, which is 8, minus 8. Isn't that going to be another 0? And in the denominator, the square root of, what's that? 2 squared times 1 squared, which is going to be a 4, minus 4. That's the square root of 0, which is the square root of 0, which is 0 over 0. That means we're good. Oh my God, but how do we deal with this beast right here? All right. Okay, it's time to use all of our tools to factoring, to all those tricks to make look like known forms. So you're gonna like this one, I'm pretty sure. All right, what do we do to begin with? Okay, u of x. Let's do a substitution. U of x, y. I'm just going to do x, y. All right? Because that's the only part that somehow repeats. I'm not going to do x y minus 2 or x squared, y squared minus 4. No, because that's not a repeating pattern. The only repeating pattern is x, y. So in this case, u of 2 comma 1, that equals 2 times 1. So I'm going to write which is 2. So I'm going to write the limit as u approaches 2. That's the square root of u minus 2 plus u cubed minus 8 divided by the square root of u squared minus 4. Where did I get this u cubed and u squared? Because if u equals xy, square it to get this term right here and cube it to get this term. That's what our substitution leads to. Well, in this case, although you could do the L'Hopital's rule, I don't recommend the L'Hopital's rule because that's going to ask you to differentiate via chain rule with radicals, and that's going to take us to where complex fractions with radicals. You don't want to deal with those. So we're going to use the factoring techniques in here. That is, do you see this difference of cubes? That difference of cubes. Whenever you have a cubed plus b cubed, so a squared plus b squared. Oh wait. A squared, ab, b squared, ab. Let me do the other one to show you the pattern. To factor sums and differences of cubes. You may have seen it before. So the forms to factor sums and difference of cubes, they all look the same. So you might have heard the SOAP approach. What does that SOAP mean? So, okay. Same, opposite, always, positive. That's what it means. Okay, what do we mean by that? Because the forms are the same. Okay, so the first sign right here is going to be the same, the plus. The opposite, and always positive for the very last term. Okay, let's look at, this is going to be the minus, okay, the difference. So same, minus, opposite, which is plus, always positive for the very last term. All right? So I'm going to factor out that difference of perfect cubes. That is equal to limit as u approaches 2. That is the square root of u minus 2 plus u, what's that, minus 2 times u squared plus 2u, plus 2u plus 4. Everything divided by, actually, I'm going to factor the difference of squares inside the radical in the denominator. That's u plus 2 and u minus 2. So that's because then I'm gonna break this up into a product of two radicals. That is the the product rule for radicals. Actually, how about we do it right now? Let me do this. U minus 2. All right, I think it's pretty obvious to see, I guess. So, and somehow I'm going to cancel the radical that cancels the 0 in the denominator. Which one is it? It's the radical with the u minus 2. All right? because that gives it the 0 in the denominator. But how do I factor out from the numerator? That's the trick. Check this one out. Have a look at this u minus 2. Okay? Have a look at the u minus 2. That equals limit u approaches 2, square root of u minus 2. Okay, do you guys agree that this u minus 2 is the same as saying square root of u minus 2 squared? Do we all agree with this? Times u squared plus 2u plus 4. That divided by the square root of u plus 2 times the square root of u minus 2. Okay, why did I do this weird trick right here? That's so we can see that this is the greatest common factor. Alright? So I'm going to factor out, what's that? So limit u approaches 2. I'm going to factor the square root of u minus 2. Let me open big parentheses here. So when I factor this one out, I'm going to be left with a 1. I'll be left with a 1. One plus 1 factor of square root of u minus 2 times u squared plus 2u plus 4. Everything divided by the product between the square root of u plus 2, u minus 2. And magic. Do you see it? Goodbye root of u of 2, goodbye root of u of 2. This is not going to be a problem anymore, so we will be able to compute the limit as u approaches 2. Alright? So let's see about it. This will be limit as u approaches 2 of 1 plus root of cube minus 2 times this polynomial u squared plus 2u plus 4. Everything divided by the square root of u plus 2. Okay, we're good to go because we will no longer get a 0 in the denominator or the 0 over 0. In fact, look at the denominator. Square root of u plus 2, that's 2 plus 2, that's the square root of 4. So we're good. And in the numerator, that's going to save a lot of work because, okay, so 1 plus the square root of 2 minus 2, which is going to be 0 times all this madness here, 2 squared plus 2 times 2 plus 4. It doesn't matter what this is because, well, root of 2 plus 2. Because all this in the numerator, it's going to go to 0. Okay, that's going to leave us with 0 plus 1 in the numerator rather. That's 1 plus 0 over the square root of 4, which is 1 over 2, which is, final answer. All right. Yes, limits with multiple variables become fun, right? Yes. All right, guys. So